Good morning, good afternoon, and good evening. Hope that you are all doing well. Here is Mariam Shref, and I would like to welcome you all to From Earth to You event organized by SEG Sohag, SPWLA Alexandria, SEG Mansoura, SEG Tanta, and Arab Guru, and AAPG Cairo, and Kuna Zayak. Today's session will be about organic shale evaluation and development presented by a special guest speaker, Dr. Ahmed Algarhy. This event will be composed of six lectures, two of which will be presented by Engineer Pietro Galli about how to enhance your resume and how to land a job interview. And the other four lectures will be presented by Dr. Ahmed Algarhy about organic shale evaluation and development. Now, please note that all of these lectures will have quizzes which will be posted on Google Classroom, mainly after each lecture, and a final exam at the end. Please join Google Classroom and do the assigned quizzes and final exam to be able to receive a certificate of completion. And please note that the passing grade is 70%. So let me begin by introducing Dr. Algarhy. Dr. Algarhy is the director of BioPetro, a nonprofit educational project. He's an assistant professor at Marietta College, Ohio, USA, where he teaches production and completion, geomechanics, and unconventional reservoir evaluation and development. He received the Regional Distinguished Achievement Award for Petroleum Engineering faculty for the Eastern North America region in 2021. Dr. Algarhy holds a PhD and a Master's of Science degree in Petroleum Engineering from Texas Tech University. Besides, he holds a Master's of Science in Petroleum Engineering and a Natural Gas Engineering Postgraduate Diploma and a BS in Mining Engineering from Cairo University in Egypt. Moreover, Dr. Algarhy has over 11 years of oil and gas industry experience with operation and service companies that focuses on hydraulic fracturing, geomechanics, and unconventional reservoir evaluation and development. Prior to working for Marietta College, Dr. Algarhy worked for Advantech International, OGS, Khalda Petroleum Company, Texas Tech University, and Solomon and Associates. Finally, he published many journals and research papers with Elsevier, SPE, SPWLA, and ARMA. And in addition, he filed 2 US patent applications to increase hydrocarbon recovery in both conventional and unconventional reservoirs. So please join me in welcoming Dr. Algarhy. So welcome, Doctor, and thank you for joining us this afternoon. Now, as a reminder, if you have any question related to the technical content of today's presentation, please feel free to drop it down in the Q&A section, and we will sure try to answer as many questions as possible. Now, without any further ado, Dr. Algarhy, the mic is yours.
Thank you, Mariam, for the presentation, and thank you for all the attendees who showed up today. Today, we have very interesting topic. Very interesting worldwide, not only in Egypt or in the Middle East. Is a very interesting topic worldwide, which is organic shale. So today we will start our series of 4 lectures. So today is our first lecture, and the title of the first lecture is Introduction to Organic Shale Evaluation and Development. So in these 4 lectures, I will try to cover the basics of evaluation process, also the basics of the development process. When we say evaluation, it means I'm trying to confirm, or I'm trying to find the good places of what we call sweet spots inside a shale play. And development means I will frack it and produce, oil or gas from it. So let's get it started. Okay, so the agenda of today, I will try to explain to you what is shale, because this is a very the most important part. We are talking about shale, so we want to be sure that we understand what is shale. Second, I will talk about shale evaluation. I will talk about the geology and source rock. What does a source rock mean? Also, I will introduce one of my professor's models. His name is Richard Bateman. Also, I will tell you something about geochem log and NMRI, or magnetic resonance imaging log. I will tell you something about coring, rock mechanics lab, geochem lab, and rock mechanics lab, and brittleness index, drilling pad, and we will tell you some basic information about shale completion, like such as well spacing. What is well spacing? What is zipper fracking? What is slick water, and so on. Okay, so number one, what is shale? Shale is a sedimentary rock. You know, we have three types of rocks. I know there's many of students from Faculty of Science, and most of you already studied geology. So, you know, we may have igneous rock, we may have metamorphic rock, and we may have sedimentary rock. When we target oil and gas, we are focused on sedimentary rock, okay? So shale is a dense sedimentary rock, and if it has organic content, long time ago, like millions of years, hundreds of millions of years ago, okay? It has a lot of organic deposits. Maybe it was forest, maybe it was animals, maybe it was bacteria, maybe anything that we can consider organic content, okay? So that deposition, I will call it source rock. This is the kitchen. This is the kitchen of the oil and gas, okay? We know later this source rock will get buried under the ground. It will go deep and deep and deep under the ground. The temperature and pressure will keep increasing over millions of years. So these organic contents will get cooked and it will become oil or gas. Okay. So before that, I mean, a migration may happen. So the oil and gas may travel or may migrate from its original place to somewhere else, what we call it conventional reservoir. Maybe a sandstone reservoir, maybe limestone reservoir, maybe dolomite reservoir. And these three types, we call them conventional reservoirs. Okay, shale, or the original place of we call it source rock. And if we develop this source rock, I will call it unconventional reservoir. Unconventional reservoir is not only shale, which is a common mistake. You know, a lot of students, they consider unconventional reservoir is just shale, which is not true. Unconventional may be shale, maybe tight sand, maybe coal bed methane. So anything that has extremely low permeability, a permeability by nanodarcy, and I cannot develop it using conventional techniques. I must do horizontal drilling. I must do massive hydraulic fracturing. So I will call it unconventional reservoir. And today we are focusing only on organic shale. Okay. So for organic shale, and we already agreed it is a sedimentary rock, and we already agreed it is, I'm trying to find a source rock, that a shale that has organic content, because maybe the shale has no organic content, so I cannot, I will not find anything in it. This is why a lot of geologists, they like to call it organic shale. I'm trying to find organic shale, not any type, not any other types of shale. Okay. For shale, I must do three things. Okay, the first one, I must do horizontal drilling. Number two, I must do hydraulic fracturing. If you will not do these two things, there is no way to produce in economic way. You will lose your money. Okay. Number three, it will be favorable if this shale is brittle. So I will use slick water. Slick water is very cheap compared with the conventional frac fluid. Okay, we use in sandstone formation, for example. Okay, guys, please, whenever you have a question, write it down in the Q&A section, and at the end of the lecture, I will answer it. Okay, so Here at Marietta College, I used to teach lectures about organic shale, and organic shale is extremely important for the United States. Why? Because more than 50% of the oil and gas we are producing here in the United States, we get it from shale plays. Maybe the situation is different in Egypt, the situation is different in Saudi or in North Africa or in Middle East in general, that most of our production, we get it from conventional reservoirs. All the countries, or most of the countries in the Middle East, they did some evaluation projects, but no country, producing in economic way. It's just evaluation because we're still in the Middle East, we are facing a problem of rare fresh water. We need a lot of fresh water to frack these wells. So in Egypt, we have a problem with fresh water. Okay, in Saudi, they don't have enough fresh water. In Kuwait, they don't have enough fresh water. In Jordan, in Libya, in Algeria, they all have the organic shale, but they don't have enough fresh water, besides some other technical problems. And also in Saudi and Gulf area and Libya and Algeria, they already have a lot of easy ones. So in Saudi, you drill anywhere, you get oil and gas, easy oil and gas. So why you waste your time and money developing shale? So maybe after 100 years you will do it. Okay. So also at the end of this group of lectures, I will cover some challenges we are facing in the Middle East. Why until today we did not develop or we did not have any big scale project on shale. Also, I will explain why shale is very successful in the United States, is very successful in China, is very successful in Argentina. Okay. This is a map of the United States. You can find shale exists everywhere in a very good quality. In the United States, we have many shale plays in many states. Also, we have a lot of huge amount of fresh water. We have, it is raining all the year. We have a lot of rains in the United States, so we don't have any problem with finding fresh water in a large amount of fresh water. Also, we don't have any problem with technology. We have the technology here in the US. We have frac fleets, many frac fleets. So we don't have any problem with the horsepower, no problem with the technology, no problem with engineers, with crews will frack with fresh water. So in the United States, it's the right place to develop shale. We have almost everything. Okay. Now let's discuss what is shale evaluation. Guys, in 2013 and until half of 2014, I moved from OGS, the training company in Egypt, the training arm of the Ministry of Petroleum in Egypt, to Khalda Petroleum Company. And I was lucky that I get involved in a project made by Khalda and Apache. And they were trying to evaluate the first shale play in the western desert in Egypt. Okay, that play is called Amun Shale. Okay, so I get involved with the exploration team, and I get very good experience with that, especially because it was in Egypt. Okay, and most of this work done by Halliburton and some other service companies did part of the work. Okay, so the first thing we need to do to evaluate a shale play, and a shale play, I mean the formation of the layer that including that organic shale. The first thing I will ask myself, am I drilled any conventional wells before, and these wells penetrated these organic shale zones or not? If yes, please show me these well logs. I need to see these well logs. So we ask to see something called quad combo. If you work for a company, whenever you will graduate and you get a job with a service company in Egypt or operation company in Egypt, you will find well logs. We use a commercial name, triple combo or quad combo. Triple combo means I want the service company, maybe Schlumberger, maybe Halliburton, for example. I want them to come and do gamma ray, to do resistivity log, to do density log, to do Newton log. We call it triple combo. I see one of you notice that triple means 3, right? But if you check the list, you will find them 4. So why I'm calling a list of 4 triple combo? The reason is I'm using the density log and the Newton log, both of them to get the porosity. So you can say it is porosity, resistivity, and gamma ray. Now they are 3. Now they are 2. Okay? If you add sonic log, if you want to measure the TDC and TDS, the shear wave and compressional wave, what we call the sonic log, now I added one new, so the triple combo will become quad. Quad means 4. Okay. Okay, so number 1, I will do a quad combo, or I will ask if there's any quad combo already done for these wells already developed. Okay, so I need to talk to the geologist and petrophysicist working for the company. Let's say I'm doing this job for Khalda, so I need to talk with geologists and petrophysicists who have good experience with Western Desert in Egypt. And I will ask them, please tell me where is the source rock. They know where is the source rock. They know how the path of migration happened. They are better than petroleum engineers in that. This is their job. Okay. I will cover this part, and then I will go to Bittman's model and geochem and NMRI log and so on. Okay, so if I get the logs and talked with a geologist and petrophysicist working for the company, and they already told me where is the source rock, I may notice a high gamma ray in that shale, in that organic shale. Guys, everybody knows that shale will have high gamma ray. By definition, shale will have gamma ray, right? But I will expect to see extra gamma ray. Why? Because the organic content will have some uranium. So this uranium will add to the gamma ray. Gamma ray, recording the emission of the potassium, of the uranium. So I will notice the uranium will be extra because I'm getting some uranium from the shale itself, and I'm getting some uranium from the organic content itself. So I will see some extra gamma ray. Okay. I will notice some high resistivity. Why high resistivity? High resistivity because it has organic content. It has some hydrocarbon, and hydrocarbon will give you high resistivity. If there is water, you will see the resistivity is will be very low. But if you see high resistivity, most likely there is hydrocarbon, but please don't get tricked. You need to check the porosity first. Okay, because if the porosity very low, you will see high resistivity, not because of the hydrocarbon, it is because of the low porosity. So you need to discuss both, to check both of them. Okay, then I need to calculate something called TOC, total organic content, or total organic carbon. Okay, the TOC, I will use some theoretical equations, a famous equation, one called Passy equation, and a second one called Schmoker equation. I will use both of them to get an idea about how much TOC exists. TOC is a percentage of the organic content exists in this formation. Is it 1%? Is it 2%? Is it 5%? Is it less than 1%? Okay. Also, I need to get an idea about the maturity. Guys, maturity means how well this hydrocarbon get cooked. If you go to a steak house and you order a steak, they will ask you, do you need it medium or well done or rare, for example. If that hydrocarbon is well done, very, cooked very well, most likely will find gas. If it is not, let's say if it is medium, you may find condensate, you may find oil. So maturity is very important. The thermal maturity is very important because this will give me an idea about what I will be producing. Guys, the price of oil is different from the price of gas, different from the price of condensate. And you need to evaluate exactly what you have. Okay. This is my dear professor, Mr. Richard Bateman. Richard Bateman has a master's degree, so I call him Mr. Richard Bateman, not Dr. Richard Bateman. He's a British guy, used to work for a long time for Gapco in Egypt, for British Petroleum in Egypt, before BP, sold this company to Dragon Oil. So a long time ago, during the 70s, Richard Bateman used to work in Egypt for BP. Okay, so Richard Bateman taught me 2 classes at Marietta at Texas Tech University during my PhD, and I noticed one of the very interesting things that he introduced a visual way to see what is inside the shale. So look to the left, look to the mouse. 9-component model. Okay, what is inside in the core? This is the solid stuff. The organic matrix, the inorganic matrix, the clay solids. Clay solids, inorganic matrix like sand or limestone or dolomite or whatever, and the organic content. Let's say this is the kerogen of the organic container, for example. Okay, all these things are solids. Look to the borders. We have the liquids. We have the, sorry, not liquids, fluids. I may have oil. I may have free gas. I may have adsorbed gas. I may have clay-bound water. I may have capillary-bound water. I may have free water. So 6 fluids and 3 solids. Okay. If you consider these 9 components, you can get a good idea about the bulk density. Look to number 1, the one in the middle. Okay, so oil, free gas, and adsorbed gas, and with the organic content, this stuff will be oil wet. Okay, the other side, the free water, the capillary bound water, the clay bound water, and with an inorganic matrix, this stuff will be water wet. Okay, so this thing will give you an idea about the wettability. Look to the one to the right, 7 components with hydrogen. So tell me which one of these 9 components, including has hydrogen. Oil, free water, free gas, adsorbed gas, organic content, organic matrix, free water, capillary bound water, clay bound water. All these things has hydrogen. So this will give you an idea about the readings of the Newton reading. Okay, and the porosity, the Newton porosity. Look to the bottom. The 3-component conductive, free water, capillary bound water, clay bound water, all the 3 are conductive, electric conductive. So this will give you an idea about the resistivity. Okay, I have 2 things radioactive. I have the organic matrix. I have the clay solids. Both of them has some radioactivity. Okay, and gamma ray will reflect that. Okay, so I told you the conventional logging we are doing is a quad combo. I will be happy to have quad combo, but during the evaluation I need to do some extra stuff, like a special log. So one of the logs I need to do, I will call it geochem logging. The geochem logging is a magic tool. It will measure the elements inside the formation, and it can measure maybe up to 16 or 18 different elements like aluminum, barium, carbon, calcium, chlorine, copper, and a lot of stuff. You see the list in the left. Okay, and This tool can translate these elements into minerals. This is a real magic. This tool do a lot of data mining, a lot of machine learning, a lot of artificial intelligence stuff, okay, to translate the aluminum into to tell you exactly what is the mineral including that aluminum. Because maybe you will have more than one mineral including aluminum. Different minerals may have aluminum. So this tool, the good thing about it, it will translate the aluminum or barium or carbon or calcium to the right mineral, okay, which is very helpful, okay. This tool will use a neutron source. The neutron source will hit the nucleus of that element, and this will excite the nucleus of that element. And after a short period of time, that nucleus will start to excite again. It will emit some gamma ray. Okay, so this tool will measure this gamma ray, and it will translate this gamma ray to the right element. And later, I will translate this element into a mineral. Okay, so this tool can tell you exactly the mineralogy of that formation. How many quartz we have, how many limestone, how many dolomite, how many different clays, how many anhydrite, and so on. Okay, so this is this tool very, very helpful. And during the evaluation process, we should do or we must do something like this. Geochem logging. Okay. There's different companies doing geochem log, like Baker, Halliburton, Schlumberger. They are the most famous three companies doing this business. Flex, this is the commercial name of Baker tool. GEM, this is the commercial name of Halliburton tool. SES and Lithoscanner, both are tools by Schlumberger. A second important tool, which is magnetic resonance imaging. Magnetic resonance imaging is a tool. We get its idea from a medical application. Guys, when someone let's say, get his arm broken, he get a recommendation to do X-ray, because the X-ray will see the bone inside your arm, for example, but it will not see the muscles, or it will not see the fluids surrounding your bone. Okay, the magnetic resonance imaging, or MRI, will do the opposite. It will not see the bone, but it will see the fluids inside your arm, for example. If someone has tumor, when someone get like a pain in his brain for a long time, and he go and check, and the doctor tell him that he has tumor, like a damaged piece of the brain, and they need to do a surgery to remove it, for example. So how we can see inside your brain? I can do magnetic resonance imaging, MRI. Okay, so we copied this application, and we do it in our oil and gas industry, mainly when we evaluate shale. Magnetic resonance can tell you something about the quantities of the fluids inside the rock, can tell you something about the properties of these fluids and the type of these fluids, can tell you something about the size of pores, the size of pores inside that formation. If you know the size of pores, you can get an idea about permeability, so you can know the permeability. What is really magic is that you can know what is movable and what is not movable, what you can produce from these fluids and what you cannot produce, and it will stay forever inside that reservoir. Guys, the reservoir now, I'm talking about shale. So the reservoir here is the shale formation, not a conventional reservoir. So in shale, in magnetic resonance, I will measure three things. Two of them, we call them T1 and T2, and both of them, they are a kind of relaxation time. And one of them, we call it D, which is diffusion. Okay, And I will have a cutoff line. This red line we call the cutoff. And what is to the right, this will be producible. What is in the left, what will not be producible. Okay, so this will give you an idea about the permeability and pore volume and pore throat and things like that. Okay, so if I use a magnetic resonance tool, I can get an idea about the fluid inside the formation. So I can identify this formation includes gas or light oil or heavy oil or movable water or bound water. How I will get this? By measuring T1, T2, and D, relaxation time and diffusion. And based on the analysis I will do for T1, T2, and D, I can get exactly the fluid, the gas, or like oil, or heavy oil, or movable water, or bound water. And also I can get an idea, a good idea about the permeability and porosity, and what is movable and what is not movable. Okay. What else is important during evaluation? I must do cooling, full size cooling. Cores will be similar to what we see right now in this picture. This is a full size core. Okay. Assume the formation, that organic shale formation, its thickness is 300 feet or 500 feet or 100 feet. If it is thick or not, I will pour all of it. Okay. So I will do a full size coring for at least one well during the evaluation. And something interesting, when I teach these things here at Marietta College, some students, they say, hey, we attended jobs at shale plays, but we have never seen them doing coring or doing geochem log or doing NMRI log. Why? The answer is they are attending fracking jobs in places they already did this evaluation long time ago. So maybe 20 years ago or 10 years ago or 5 years ago, this evaluation already done. And now we know exactly what is inside this shale formation. So there is no need to waste your money in doing evaluation again. Just you drill horizontal wells, you frack it and produce, and that's it. Okay? So after you do the full size coring, what you need to do? I will invite two companies. One of them will do something called rock eval. They will do pyrolysis testing. And I will explain what is pyrolysis testing. And I will invite a second company to take some cores, some small cores. The cores like, let's say, 3-inch by 1.5 inch, small ones, okay? So the second company will get some cores from different depths, from different places here, and it will do rock mechanics testing. It will tell me the rock mechanics properties. Okay. So number one, the rock eval company will do something called S1. Will measure something called S1 and S2 and S3. What is S1? S1 is the amount of free hydrocarbon, gas or oil in the sample. This is free hydrocarbon. S2 is the amount of hydrocarbon generated through thermal cracking of non-volatile organic matter. Guys, this is pyrolysis test. Pyrolysis test means I will heat this core until I will burn it. But before totally burning it, I need to do this burning slowly. Okay, because S1, I need to measure S1 first, then I will measure S2, and S3, this will be the amount of carbon dioxide will get generated from that burning, from the S1 and S2. Okay, and I will do this for many samples, like the samples you see in this table, for example. Then you will look to the mouse. Then you will plot these something called the oxygen index and the hydrogen index, and you will do something called Van Krevlin diagram. And I need to know this fluids, these hydrocarbons, if they are type 1 or type 2 or type 3 or type 4. Guys, I want to know whenever I will produce from this location, I will produce oil or condensate or gas. I need to include this in my study because I will invest billions of dollars in that location, and I need to know exactly how much money I will get. And again, the price of oil is different from the price of gas, is different from the price of condensate. Also, I need to have a clear vision what will be the average prices within the coming 5 years. Why I need to do this? Because I will invest a lot of money and I don't want to lose my money. Okay. This is the second company. They get many cores, many samples, okay, and they will measure the mechanical properties. Mechanical properties like Poisson's ratio, like Young's modulus, like the compressive strength. Okay, so here there's a list of cores, and each core has a, we measure its depths, the length of the core, the diameter of the core, and the UCS, or the compressive strength, and Young's modulus and Poisson's ratio. Why this is important? This is important because this will help you to design the fracking job the right way. I will be happy if I have brittle formation. Brittle formation means Young's modulus is high and Poisson's ratio is low. And I need to do something called brittleness index. Whenever I have higher brittleness index, I will be more happy. It means whenever I will do fracking, I will produce more oil and gas, more hydrocarbon. Okay, so I need to do some calculations to calculate the brittleness index. Okay, and here we see the some stuff from the pyrolysis testing for the rock eval from the rock eval company, and the last one to the bottom right. This is Young's modulus and Poisson's ratio. This will give you an idea about the brittleness index. Okay. So whenever I have, this is this work presented by a guy used to work for Halliburton, maybe 10 years ago, or maybe 15 years ago. We call it, his name is Richard Rickman. We call this Rickman equation or Rickman model, okay? And here, I need to know, based on the Young's modulus I measured and Poisson's ratio I measured, for sure what we are measuring, if you are measuring this using the TDS and TDC, using the sonic, this will be dynamic Young's modulus, and I need to convert this dynamic Young's modulus into static Young's modulus. This is why I will be happy if I have a report from a rock mechanic lab, because what the rock mechanic lab will measure, it will be the static Young's modulus. And this is what I will use in my fracking design. Okay. Again, the brittleness and understanding of Young's modulus and Poisson's ratio you have, it will help you to select the right completion strategy you will do. It will help you to select the right frac fluid you will be using. If you have high Young's modulus and low Poisson's ratio, you can use slick water. And I will explain what is slick water very soon. If brittleness index is very low and Young's modulus is very low, like less than 1 million psi, for example, so I must use cross-linked gel or hybrid frac fluid, like cross-linked gel and slick water in stages. Okay, so this information from the Western Desert in Egypt. We were trying to evaluate Amun shale formation. Okay, there's a lot of good things about it. It will produce oil or condensate. We have high brittleness index. We have a conventional behavior, which is some tiny sandstone formation trapped inside the shale, and these sandstone formation include a lot of condensate. We call this conventional behavior. But the main problem with that formation in the Western Desert that it has very low reservoir pressure. If you have low reservoir pressure inside the shale, this is something bad. This is bad news. And this is why we get a lot of debate if this formation is good to develop or bad to develop. Okay? Guys, whenever we say development, all the time think about evaluation, but also don't forget to think about the oil price. Oil price will be the key. Okay, if the oil price is very high, I may invest money in low quality shale play, for example. Okay, let me tell you something about drilling pad. When we drill shale, I need to drill more than one well from the same location. That location I would call it drilling pad. I may drill 2 wells, 3 wells, 4 wells, maybe up to 12 wells from the same place. That place, look at the mouse. That place, I will call it drilling pad. Okay, do you know the pad of the mouse? This is a pad. This is my mouse pad. Okay. So it is, a drilling pad is a small location, and we will drill more than one well from that location. In my class, I used to ask my students how many drilling rigs I need to drill 6 wells. Because in this picture, if you look at the mouse, you will see 3 wells moving to one direction and 3 wells moving to the opposite direction. So from one place, from one drilling pad, I drilled 6 wells. How many drilling rigs I need? And one student say, hey, just 1, and the student said 2, maybe 6 or whatever. But the right answer is we use only 1 drilling rig, and we move the drilling rig, we push it, we slide it slowly from the top of one well. When we drill the surface section of a one well, then we put the casing and semen and we secure the well. Then I will slide the drilling rig for a few feet and make it at the top of the neighbor well, which is maybe like 10 feet difference from the well, from the first well head. Then I will drill the surface section. Then I will do the casing and semen, and then secure the well. Then slide the drilling rig again, and make the 3rd well, and so on. And after I reach to the last one, I will drill the surface section. Then I will do the intermediate section. Then I will move backward. When I reach the first one, I will do the intermediate section. Then I will do the production section or the lateral. Then I will keep moving forward until I finish. So we use just 1 drilling rig. Okay, and this operation we call it rig walking. It's very interesting whenever you know that the rig can walk, has legs and foot and walk. Actually, it is not legs and feet. It is just we slide it. And this sliding takes hours. Maybe we need like 8 hours to slide this drilling rig for maybe a few feet, because safety, we may collapse the drilling rig if we move it faster. Okay. Now let's get a general idea about shale completion. Guys, in this lecture, I will try to introduce a lot of stuff to you. And starting from the 2nd and 3rd and 4th lecture, I will repeat these things again with more and more and more details. Okay? So let's talk about shale completion. I'm not sure if this will work or not, but let me try. See? Guys, the job of that guy, we call it fluid technician. Why I'm showing you this? Because this is the frac fluid we use with sandstone formation. This is a conventional frac fluid. If you go to the Western Desert in Egypt and attended a frac job with Khalda or with Badruddin or with Agiba, for example, and you were fracking a sandstone formation, you will find them using a fluid like this. Okay, this fluid is fresh water with KCl, with guar. Guar is something similar to starch. Okay, and guar we use it also in a lot of foods. Okay, and we use something called cross-linker, and we use a lot of chemicals. Okay, a lot of chemicals to get something like this. Okay, so long time ago, I know that the service companies were very happy because if the frac fluid is expensive, they will make a lot of money. No problem. You will order a lot of stuff and they will get it to you, and they will get a lot of you. They will get all the money from your pocket, right? So this gentleman, his name George Mitchell. George Mitchell, he born here in the United States, but his dad and mom were Greece. So they were immigrants from Greece. Okay, so George Mitchell has a little company in the Barnett Shale, and Barnett Shale is south of Dallas, and Dallas is a big city in Texas State. Okay, so George Mitchell get a crazy idea, and he said to his engineers, I wanna inject just fresh water in a very high rate like 100 barrels per minute. If you attend a conventional job in sandstone formation in Egypt, you will find they are using a rate of 20 barrels per minute, 25 barrels per minute, 30 or 35 barrels per minute. So this is the maximum they are using. Maybe they will not go beyond 35 barrels per minute. But George Mitchell tried to use 100 barrels per minute, and this was really crazy and challenging idea. Okay, so some of his engineers told him, hey, to inject 100 barrels per minute, we will generate a lot of friction inside the tubing, and we cannot do that. So again, the idea is he want to inject just fresh water, no chemicals with it. They want to inject something cheap compared with the conventional frac fluid you have seen in the previous video. They want to do something cheaper. Okay, so he said, okay, I will inject just fresh water with in a very high rate, like 100 barrels per minute. So one of his engineers told him, hey, you will generate a lot of friction. He said, hey, friction, we can fix that by using friction reducer material. So I will add a chemical to it to reduce friction. We call it FR, or friction reducer. Okay, so this recipe or this mixture, we call it slick water. So slick water is fresh water plus KCl, because almost I add KCl to any type of water I'm using in our oil and gas industry. So fresh water plus 4% or 7% KCl and friction reduced. Okay, so they did this trial maybe 30 years ago in at Barnett Shale in south of Dallas, Texas, and it got amazing success. Guys, it was great success whenever they used the slick water. The main reason because the formation was very brittle. At that time, it was just a trial without any expectation of what would happen. They did not know. They just tried something, weird idea, and it works. Okay, so all of us until today, we should say thank you to George Mitchell, because he introduced this idea. And almost all the companies here in the United States, most of them, now they are using slick water. All companies, they adopted slick water in fracking shale. Okay, if your shale is ductile and not brittle at all, maybe slick water will not be an option, but we will discuss this later. Okay, so after knowing what is slick water, let me tell you something about what is zipper frac. Guys, zipper means in Arabic means susta. So the zipper you have in your jacket, for example. So we faced an operation problem, and a zipper frac solved that problem. The problem is I'm using two companies in the location. A company do pumping, like they pump the frac fluid, and the second company they do plug and perf. They perforate and set a plug between each stage. So this is well number one, this is well number two, and here I will frac this part first. I will call it a stage. Then I will have a little space between the first stage and the second stage. Then I will do the third stage and so on until I will frac all the horizontal lateral. Okay. So whenever you do this and you have two companies working in the location, one for pumping, one for fracking, and one for plug and perf, they do that using a wire line. Okay, they are two different companies. So you may have, let's say, Schlumberger for fracking or Halliburton for fracking, and you have a different company for wire line to do a plug and perf. So the question now is, during the time that the pumping company pumping the first stage, what should be the second company doing? Assuming I am fracking just one well, I'm working only in one well. The answer is the second company will be doing nothing. They will not do anything. They will just wait until the first company finish their job. Then the second company will do their job. And during that time, the first company will do nothing. Then they cannot work at the same time. Like two companies and they cannot work at the same time. Okay, so assume I will frac 4 or 5 stages per day. If I can find a way to make these two companies work at the same time in parallel, I can double the number of stages and frac. Okay, guys, in the Middle East or in Egypt, for example, when we frac with the first light of the day. We don't like to frac during evening. There's the regulations in Egypt. Okay, but fracking in the United States, we frac 24 hours a day. We frac 7 days a week. So if you have a fracking project and this project will stay 20 days fracking, I will keep fracking without stopping for just a minute. I will not stop. If there is no technical problem, I will keep that job going on. Okay, so some engineers, they develop a new technique, and instead of fracking one well at the same at a time, I can complete 2 wells at the time. So I will have 2 neighbor wells, well number 1 and well number 2, and I have 2 companies working. Whenever the pumping company will work in well number 1, the plug and perf company will be working at the same time in well number 2. Then they keep switching together. Well, the second company will go to well number 1, and the first company will go to well number 2, and they keep switching. Okay, so the fracking company will start here. Look at the mouse. Will start here. Then we'll move to the second well. Then we'll go back to the first well. Then second well. Then first well. So this shape looks like a Z shape, or looks like a zipper shape, similar to the zipper you have in your jacket. Okay, so this is why we call this technique zipper frac. I can frac 2 wells at the same time. Okay, the problem is, when we frac in shale, I can frac 2 or maybe 3 wells at the same time, but we are using different terminology. We are using different names for things that are not common in conventional frac. For example, when I frac, I need to design for something called complex fracture network. When you frac sandstone, we will never use a term like this. If you frac limestone, if you do acid frac for limestone or dolomite, for example, you will not use complex fracture network. We use this only with shale. If you also, I will design for a block or a volume, I will frac it at one time. We call it stimulated reservoir volume, SRV. So this terminology, I will not use it in convention. Okay. Well spacing, I need to design what should be the right distance between these two neighbor wells. I'm not talking about the distance at the surface. I'm talking about the distance between the laterals of the formation. We call that well spacing. I need to discuss how many stages I will do per one well. Look to the mouse. This is one stage. And each stage consists of a group of clusters. Okay, so look to this picture. It seems like this stage 1, 2, 3, 4. It seems like there are 4 clusters, like 4 fractures in one stage. Maybe one well include 10 stages, or 15 stages, or 20 stages, and maybe one stage include 5 clusters or 10 clusters. It is your design. Okay. Also, I need to discuss the volume I will inject for every single stage. Okay. So I already defined what is a zipper frac. I will tell you what is the benefits of zipper frac, guys. We are close to finish. So if you have any question, please write it down. Write in the Q&A section. Okay. Okay, so the advantages of zipper frac, as I told you, zipper frac reduces the cycle time because it will increase operation efficiency. Instead of the 2 companies cannot work at the same time and just one company can work at a time, now the 2 companies can work at the same time. Okay, so this is very valuable. And actually, we can double the number of stages I can frac every day because of that. Okay. The zipper frac increased production rate. Guys, one of the good news, one of the good surprises, when we did the slick water, we got a lot of production. And later, we started to study why that happened. Now, when we used zipper frac, most of the companies, they reported increase in productivity. And at that time, we did not know what was the reason. Now we know the reason. Now we have explanation for everything because there's a lot of researchers, there are a lot of PhD students working on it. There's a lot of master degree students working on it. There's a lot of experts inside companies working on it. So now we understand. But when we try it the first time, we see that we get 30% to 40% production increase, and we don't know why. And we ask other companies, hey, have you tried zipper frac? Yes. Have you get increase? They say, yes, we get increase. So most of the companies, they get increase. Okay. So the disadvantages is, number one, at that time, we did not know the reason why we get a production increase, but I cannot consider that disadvantage. If I get extra money, but I don't know why, I will not consider this disadvantage. I'm happy that I get something else. Okay. Okay. So whenever the hydraulic fractures they are close to each other, if we have 2 horizontal wells beside each other, and when this stage is close to each other, sometimes if the fractures get closer, the stresses, they get something called stress shadowing. So the fractures start to bend. And this bending, because of the stress shadowing, may do pressure drop inside the fracture. This is a problem, but we do a lot of simulation to minimize the impact of this. Okay. Finally, this is a conclusion and the end of today's lecture. So the conclusion is, now I am evaluating the source rock. I'm evaluating the organic shale, and this is a source rock. Before, I was producing from the conventional reservoirs, means after the hydrocarbon migrate from the source rock. Now I am developing, or I am fracking and producing from the source rock itself, or the organic shale itself. It should, I will be happy if this source rock include the good TOC, total organic content, of total organic carbon. Okay. Also, I would be happy to understand the thermal maturity, so I can do my calculation. Am I having oil or condensate or gas? I would be happy if I have good brittleness, if this formation brittle. or this will be successful in fracking, easy to frack. Also, if I have enough fresh water in that place, okay, for hydraulic fracturing. Also, if I have enough horsepower, because in some big jobs I may use 40,000 horsepower. Guys, I will tell you something very funny. And 10 years ago, I believe if we get all the pumps that Halliburton and Schlumberger, because then 10 years ago only Halliburton and Schlumberger, they were fracking in Egypt. No other company. They are just two companies. Okay. If you collect all the pumps they are using for fracking, it will not be 40,000 horsepower. So if you want to do a big job like what happened here in the United States, and you need 40,000 horsepower pumps, I will not find that in Egypt. If I collect all the pumps from all the companies working in fracking at that time, I will not have it. I'm not sure what is the situation now, but still 40,000 horsepower is like you need 20 pumps. I'm not sure if Halliburton, Schlumberger, and Baker all together in Egypt have 20 pumps or not. I'm not sure. Okay. Also, I will be happy if the oil and gas in a good price. A price more than $40 is a good price in the United States, but in Egypt, I believe we need maybe like we need the oil price to be something like 70 or something like that, $70 to think about shale. Okay, this is all what I have for you today, and I'm ready to answer your questions. Mariam.
Thank you, Doctor, for this informative session. Now we'll be answering some questions from the audience. The first question is that can we make polymer flooding in unconventional reservoir, mainly organic shale?
We cannot do that. The reason is shale has extremely low permeability. Guys, we do a lot of experiments in the lab, and a lot of students, they get their PhDs in lab work, and they do like water flooding for shale or polymer flooding for shale, and these things look funny because we know that we cannot do this in the field. Why? Can you imagine if you have a shale play or a shale sweet spot, and the permeability is 100 nanodarcy, or something between 100 to 500 nanodarcy? How you want to do water flooding? How you want to do polymer flooding? It is you can say it is impossible.
Okay, thank you. The second question is that why is the sonic log separated from the nutrient and density, although it is a porosity tool like the nutrient and density in the quad combo?
Okay, so this is a very good question. Let me go back and show you this. Guys, the triple combo, this is the basic group of logs we need to do. If you measure the gamma ray will tell you something that, hey, maybe this section is shale, and if you have low gamma ray below it, maybe this is a reservoir. But I am not sure if it is a good reservoir or not. Okay, so gamma ray will tell me if this is a possible reservoir or not. Okay, then I will do the resistivity, because the resistivity will tell me if I have very high resistivity, this is hydrocarbon. If I have very low resistivity, this is water. So it will tell me exactly if gamma ray told me this is maybe a reservoir, but I'm not sure if it is a good or not or bad. I will do a resistivity to know what is inside that reservoir. Now I know there is high resistivity. High resistivity means there is hydrocarbon, but wait a minute. Maybe it's a high resistivity because there is no porosity at all. Maybe the porosity is extremely low. So maybe the resistivity will mislead you, will give you wrong information. You have high resistivity and you say, hey, this is hydrocarbon. But the answer, no, this is not hydrocarbon. The resistivity is high because the porosity is very low. And you do not know that. So you need to have something to tell you the porosity. Okay. And I have two techniques. one using the density and one using the Newton. And most likely we use average between the density porosity and Newton porosity. So this is the minimum set of logs that can give you something valuable to evaluate a formation. Okay, but now you have no idea about the mechanical properties of that formation. Okay, so whenever we do sonic log, the sonic can give you an idea about porosity too. So it will confirm the porosity you get. Okay, but mainly the sonic will give you some information about the mechanical properties. You can get the Poisson's ratio in a good accuracy using the sonic log. Also, sonic log may help you to know the direction of the minimum and maximum horizontal stress, which is very important to know the direction that you will drill your horizontal well, or yes, to know the direction of the horizontal well you want to drill. And finally, you can get the dynamic Young's modulus, but remember, the Young's modulus you will get from the sonic is dynamic, which is not very accurate, and you need to find a way to convert it into static Young's modulus. Okay, so I may do only triple compound. I will say, hey, is this enough? And this is all what I want, or the case I have. I may say, no, I need to do quad because I need some more information. I wish the answer is clear.
Yes, thank you. Now, can we or do we need to inject proppant while performing the hydraulic fracturing for shale or organic shale completion?
Yes, we inject proppant, but the amount of proppant we are using, it will be different based on my understanding to the mechanical properties of the formation. For example, if I have a brittle formation, I will inject smaller amount of proppant. If I have a ductile formation, ductile shale, I need to use more proppant. And most likely I will use smaller proppant. Like I have a lot of proppant in my office. You know, I'm teaching hydraulic fraction, so I have a lot of samples. So this powder, these little things, we call it proppant. Okay, the proppant I will use with shale is a very small proppant. We call it 100 mesh. Most likely, I will use that 100 mesh proppant, but you know, this is not a rule of thumb, but you know, this is what is common. Okay, so the answer is yes, I will use proppant, but the amount of proppant and the size of proppant will be different based on the case.
Great. We have another question. Can we make hydraulic fracturing with the foam in shale?
I believe there is no problem to do it. I mean, mainly when we use the foam, mainly because we are facing a low pressure reservoir. So if you have low pressure reservoir, it is recommended to use foam. Okay, I don't see any reason that we cannot use foam in shale if I have the same problem of low pressure. If that shale has low pressure, I may use foam for it. But you know, what I can say is this is not common. Most likely, what is very common that we are using slick water. Slick water. This is you can say 99% of the shale we are doing, or 95% of the shale we are fracking, we are using slick water. Just water with KCl and friction reducer. That's it.
Okay, thank you. Now, our last question for today. Can you please briefly re-explain the geochem logging?
Okay, geochem logging. So geochem log, as I mentioned, you know, very smart tool. We are using a source of neutrons, and these neutrons may be fast neutron, maybe slow neutron. Okay, and this neutron source will go and hit the elements inside the formation. Okay, whenever I hit that element, I hit the nucleus of that element. Okay, and I will read the gamma ray emitted from that collision. Okay, so the neutron from the source I have in my tool will go and hit the nucleus of that element, and based on, and I will record the gamma ray emitted from that nucleus during the de-excitation. Okay, so like you hit something, and this something start to vibrate, and over time it will relax. So you excite the nucleus, and over time this nucleus will relax again, and will during the relaxing it will emit some gamma ray. So the tool will measure this gamma ray, and it can differentiate between the gamma ray emitted from the aluminum, the gamma ray emitted from the barium, the gamma ray emitted from the calcium, and later the tool also can translate this element into a mineral. And this is the most important part. The tool will tell you how much the aluminum or barium or carbon or calcium or whatever the element. But what is more important, that the tool will translate this based on special techniques and data mining techniques. It will translate this into a mineral. Then you will have something like you get a sample from the formation, and you did analysis for it inside a chemistry lab, and now they are telling you, hey, there's, let's say, this amount of quartz, this amount of limestone, this amount of dolomite, this amount of anhydrite, this amount of different types of clays, and this amount of organic content, and so on. So it is very advanced tool and very expensive tool. So the geochem and magnetic resonance imaging tool, both of them, they are expensive. I wish this is a simple and easy explanation for the geochem.
Yes, great. Thank you, Doctor, for your time, and thank you for answering our questions. And thank you to everyone who attended and participated in today's session. Now, don't forget to check Google Classroom for announcements regarding quizzes. And as a reminder, we still have 3 lectures with Dr. Algarhy about organic shale evaluation and development, and 2 lectures with Engineer Pietro Galli about how to improve your resume and job interview performance. So basically, the event will be held between Friday, December 10 and Friday, December 17, with no lectures on Saturday and Wednesday. By this, we conclude today's session. Now, have a nice day and stay safe.
Thank you very much, and see you on Sunday. Thank you.